Rates, yeah. You want to draw pictures on these. These are interesting. They can be tricky sometimes. So I always recommend you draw a picture. It's always going to be some idea of some physical object that's changing. You're going to use an implicit differentiation every time. You're going to plug in what they gave you and see what you have, and then reevaluate. Sometimes you're going to find you have too many variables. You have to go back and reevaluate something else. First one's pretty straightforward. A pebble drops into a pond and creates ripples. There's my pond. There's my ripples. Okay? The pond has a radius that's increasing at 1 feet per second. You can't really draw that. What you can draw is this. When the radius is 4, how fast is the area changing? How fast is the area changing? So there's your first clue right there. What formula are we going to use? Area of a pond with ripples coming out.
That's a circle.
That'd be a circle. Area of a circle.
Squared.
Pi r squared. There we
Pi
go.
r round.
Pi r over pi r round. Pi r squared. This is the formula we're going to derive right here. Now notice the other fact I've written down. You want to write down every fact they give you. You know the radius is 4, so you're going to write that down too. I didn't write that down. I should have. You know the radius is 4. You know dr dt is equal to 1 feet per second. Where did that come from?
DRDT.
Yes, where did that come from?
That's the derivative of the distance. Over time.
The rate of what?
The area.
Change of what? Not the area.
Radius.
Change in the radius. The radius
Radian.
is increasing at 1 feet per second. That is dr dt. That's what that is. The change in the radius. So make sure you get this idea. Derivative is slope, and slope is the word for rate of change. So every time I'm deriving something, whatever variable I'm left with, dr dt, dA dt, d whatever, that's the change in that real world thing. If the radius is increasing at 1 feet per second, that is dr dt. Okay with that? Change in the radius with respect to time. So we're going to derive this equation with respect to time, giving us the derivative of A with respect to time is dA dt. That's where that came from. Nothing to write. I already wrote everything down. I just want to show you other pieces. Okay, so the derivative with A is dA dt. The derivative of this equation with respect to time, well, that comes down, giving me 2 pi, 2 goes to 1, dr dt.
Are you treating the A as a Y?
So I'm not treating anything as a y, and I guess subconceptually, yeah. But the whole idea of y and x are gone. We may have 10 different variables.
So you're doing Y prime on everything?
You're not doing y prime.
Oh.
That's what, you're going to do d whatever the letter is with respect to time.
Okay.
So this is another reason not to be using the y prime, because this gets confusing if you don't. Okay, you want to use dA dt. You want to use dr dt. On the back side, I want to have dH dt. Okay. So here's my equation, derived, and now I can talk about how fast is A changing, the area changing, with respect to time. I could also, if I wanted to know how fast the radius is changing with respect to time, I could solve for any of these. The values they gave me were that the radius was 4, dr dt was 1, and so I'm left with dA dt alone. So the area is changing at a rate of 8 pi feet per second. And so this area would be 8 pi feet. Should be 8 pi feet squared. So about area. Well, let me think for 1 second. Area is changing at a rate of. I'm not going. Don't quote me on that one yet. I'm going to get that see. I think it would still be linear, so I think it would still be 8 pi feet per second. Okay? That's an easy one. Let's flip it over.
Let's do a hard one.
Let's do a harder one. Given a cone with a height of 10 feet and a radius of 5 feet, find the change in volume, and the change in radius is 3, and it should say when the radius is 3 and the change in radius is 4 feet per second. Okay? So I draw a picture. You can draw an inverted cone, a regular cone. The idea is we're filling up with water. Okay? These are things you know. How high is it? 10 feet. So it's 10 feet high. How wide is it? 5 feet. And the question is, when the water is sitting at about this level in here somewhere, okay? And the radius is 3 instead of 5. So we're filling it up, but we're not all the way full. When the radius is 3 and the change in radius is 4 feet per second, how fast is the volume changing? That's the question we're asking. How fast is it filling up? So, we've got our picture drawn, we have some ideas here. We're going to find dVdt when R is 3 and when drdt is 4. When the radius is 3 and the change in the radius is 4 feet per second. So the volume of a cone, that's the first thing we find, volume of a cone. Anybody know what it is without looking?
Pi squared h,
That's volume of a cylinder,
third of
A
it.
third of it.
third of that. Okay, 1/3 of pi r squared h. So we derive that bad boy, and we get dV dt. That's derivative of volume. The 1/3 pi is a constant, so just kind of ignore it, bring it outside, and just derive the part inside. This is product rule. So r squared h becomes 2r dr dt h, I missed an h right there, plus r squared dh dt. Do you agree with that? Everybody okay with that?
The third and the pi,
They're constants. They can come out.
So like whenever we did y,
both of them.
you had to do your dy dx.
Yes.
But now you have to do that with the x
Every
too.
single letter you see. Because it's not dx anymore, it's now dt. Every one of these related rates problems is what's happening with respect to time.
Why didn't we do that with the x then?
Because we were deriving with respect to x, so dx over dx was 1. It went away. If I had a t in here somewhere, it'd be dt over dt, and that would go away. I don't have a t in here anywhere.
Okay.
That make sense to you? Okay. So this is correct. 2r dr dth plus r squared dh dt. If I'm deriving out these two pieces right here.
Yes.
Okay. I threw these notes together right before you guys walked in, so sorry for some mistakes.
Brilliant.
Look at what we have left here. I'm trying to find dV dt, so that's correct. I know R. I know
dr over
dr dt. I don't know H. And I don't know dH dt.
We do know h. Oh, we don't.
We don't know H.
Thought it
We
was
could
10.
probably find
I thought it
H.
was 10.
No. 10 is the height of the whole cone.
We want the height of the water.
I want the height of the water. Right. The question is, at this point in time, right here, well, H is not 10 and R is not 5 at this point. Okay.
What do we do?
So that's where I said in the previous page, you plug everything they gave you, and then you go back and see if things don't work out right. You may have to rework the original equation and rederive it. Okay? So let's
So
go
the
back
second
and look at this.
derivative?
Not second derivative, rework the whole equation and start from scratch. We got to the end, it's like, dang it, we can't solve this.
Just do the same.
We have too many letters.
Okay.
So we have to get rid of a letter. We have too many letters because we had dr
Yeah.
and dh and r and h. That's too many letters.
Too many letters.
I can't have r's and h's. But I could rewrite this to where everything was just an R. Notice, do you see a property, a ratio, a proportion that relates H
That's 1/2
to R?
Or two.
to the, yeah.
So
What if
H,
it's
The
not?
height is always twice as,
H is twice the radius, isn't it? Or radius is a half of the height. Either way would be fine.
Well, let's do 2.
Let's do the 2R.
No fracks.
Fracs, yeah, they're no fun. Another reason not to mess with this is because I still don't know, look at this, I still don't know
H.
H. I do know
R.
R right there, okay? So, we've got this now. Take our equation and rewrite it as,
2/3 pi r cubed.
I replace the H right here with 2R. Sorry, y'all can't see that. I replace the H, 1/3 pi r squared H with 2R. So we get 2 in front, distribute the R, and I have 2/3 pi r cubed. Everybody follow what just happened right there? I had 1/3 pi r squared H, replace the H with what H is. H is 2R, so put that where the H is. Distribute, and I'm left with that. Rederive it with respect to t. So dv dt is derivative volume with respect to time is dv dt. Derive this. 3 comes down. 2 times 3 divided by 3 is 2. Pi is constant. R squared. dr dt. Now I can plug in what I know. I knew that R was 3. I knew that dr dt was 4. So this is going to be 9, 36, 72 pi feet per second.
Cubed per second.
I'm going to have to look that up. Again, I don't remember. I'm thinking the rate of change of volume probably is still cubed. I just need to make sure. I'm going to look that up here in a second.
but since that other one was just.
Say, the other one could have been squared too. I need to look both those up and see. Okay? So that's what we're doing the next couple of days. Everybody say woo woo. Yes.
Woo woo, the cops are coming. They're putting all those drugs, can we? Oh, I don't know.
Oh, the cops.
All right, so let's go try some of these out and see what happens. Let's start with 15. We're going to come back to 13 later. Let's start with 15.
What is it?
2.2, yes ma'am.
Yes. What page is this page? 54, but there's